Hello, this video is for Chapter 9, STA2023. We're going to be talking about inferring population means. So in this case, similar to Chapter 8, we're going to be looking at your SE, and the formula for your SE, your standard error, will be the standard deviation divided by the square root of n. So in this example, a student's iTunes library of MP3s has a very large number of songs. The mean length of the song is 243 seconds, and the standard deviation is 93 seconds. The distribution of song length is right skewed. Using the MP3 player, this student will create a playlist that consists of 25 randomly selected songs. So is the mean value of 243 seconds an example of a parameter or statistic? Now remember, parameter is everybody, statistic is sample. So in this case, it's a parameter because it's the mean of all the songs in the library. What should the student expect the average song length to be for his playlist? Close to the average of all songs. And what is the standard error of 25 randomly selected songs? So because we're selecting 25, our n is 25, our standard deviation is 93, so to find our standard error, it's 93 divided by the square root of 25, which is 18.6, and you want to practice that in the calculator. So again, we're going to review some things like the essential limit theorem, which talks about if you want to assume your data is normal, you have to pass these three conditions. Your data is random and random sample and independent, normal, and you have a large population, and the population has to be greater than 10 times the sample size. So here, we're not going to be doing a Z distribution, but we'll be doing a T distribution. So let's talk about what's similar and what's different about the two. Notice that both of them are normal, got that symmetric shape, but the difference is a normal distribution is higher and a T distribution is lower. But really what that means is a T distribution is more forgiving. In a Z distribution, most of the information is in the middle with a little bit on the outsides. A T distribution is flatter, where less is in the middle and more on the outside, which makes it more forgiving. And the reason why we use a T distribution versus a Z distribution is a T distribution is good for small samples. That's going to be our issue, small samples. So, and again, some more information. And then we're going to be talking about something called degrees of freedom. And degrees of freedom is n minus 1. N minus 1. So your sample size minus 1. So when we figure out our statistic, instead of doing a Z as in zebra statistic, we'll be doing a T statistic. So it'll be x bar minus mu over your standard error. And your standard error, again, is standard deviation divided by the square root of n. Notice we're using x bar and mu, not p hat and p, because we're talking about numbers, not percents or decimals. And then for the confidence intervals, make sure that it's random and your data is normal. And when I say normal, I'm looking for a sample size of at least 25. At least 25. If your sample size is 25 or larger, you're good to go. You can assume it's normal. If it's under 25, you're going to have to do a histogram to see if your data is normal. Because if it's under 25, it needs to be normal. But as long as you have 25, you can assume that the data is normal. That's what's nice about a T statistic. And when we do a confidence interval, it's going to be x bar plus or minus T star, we'll talk about T star in a little bit, times the SE. So for example, suppose we want to collect a sample of 30 iPads and wish to calculate a 90% confidence interval for the mean life of the battery. The sample average of time that the iPad battery lasts is 9 hours with a standard deviation of 1.5 hours, and we want to calculate a 90% confidence interval. So in this case, our x bar is 9, standard deviation is 1.5, our sample size is 30, but if we want to find the confidence interval for 90%, we also need the T star. Now, T star we'll get from a table once we have two pieces of information. Those two pieces of information is what percent confidence, which in this case is 90, and your confidence and your degrees of freedom, n minus 1, 30 minus 1, which is 29. Now we'll go to the table. Here's our table, our T distribution table. Notice we have the confidence interval on the top, 90% confidence interval, and then the degrees of freedom on the side. So we're looking for 90 and 29. 90 and 29, which would be right here, 1.699. Now I do want to point out something about the table. After 30, it jumps from 30 to 40 to 50, and you don't have any in-betweens. So what we can do is, if we're looking for, let's say, a degrees of freedom of 35, it would be between these two. We can just pick a number pretty much in between these two, or a little closer, or this one or that one, because they are very close. because with the table we're going to have to estimate a little bit. Okay, so we now know our x bar, which is 9, our t star we just found at 1.699. Be careful when you find your SE, it's the standard deviation divided by the square root of n. Work that out. We have 9 plus or minus 0.4654, which gives us 8.5349 and 9.4654. So we are 90% confident the average lifespan of the iPad battery is between 8.54 to 9.47 hours. So let's do an example from scratch and put all of this together. All of your calculator steps to work on that are here. And I'll go ahead and demonstrate that for you. So again, all the steps are here, but I'll go ahead and demonstrate that for this example. So remember, we're doing a t interval. So we bring up our calculator, turn it on, we go to stat, test. We're looking for t interval, which would be number 8. And then it's going to ask us for data or stats. Data means we put the data on a list. In this case, we don't have a list of data, but we do have stats. So we're going to choose stats. And then we're going to fill in our numbers. So n, wait up a little bit. N would be 9. Our original standard deviation is 1.5. Our n is 30. And confidence interval is 0.90. And we go to calculate. And they should be very close. Now remember, they may not be exact because we have to round a little bit with the t star. So they may not be exact, but they will be very close. They will be very close. Okay, so let's do our first example. All the confidence interval, HO, HA, all that stuff remains. Our conditions. And remember your conclusion chart. So let's do this first example. It is reported that Americans work an average of 7.5 hours per day with a standard deviation of 1 hour. A random sample of 10 Americans had an average of 8.5 hours per day. Is there enough evidence at the 5% level that Americans work more than 7.5 hours per day? So let's be organized. Our mu, 7.5, the average of all Americans. X bar, 8.5. Our standard deviation is 1, N is 10, and our alpha is 0.05. So for HO, which we've worked on before, we're going to say equals. HO is always equals, but in this case we're not doing proportions, we're doing numbers. So it's mu equals 7.5. The average hours of work for Americans is equal to 7.5 hours per day. And in the problem we're looking for more than, so mu is greater than 7.5. The average hours of work for Americans is greater than 7.5 hours per day. So watch the details, mu, not p this time. Our conditions, number 1, it's got to be random. That was stated. To be normal, it has to be greater than 25. Now, we only have a sample size of 10, which means we have to make sure it's normal. In this example, we'll just assume it's normal. But remember, for a t-test or for your projects, you want greater than 25, greater than 25. And then we'll make sure our population is greater than 10 times the sample size. Population is all American workers. Is it greater than 10 times our sample size of 10 of 100? Yes, there are more American workers than 100. Then we work it out. In order to work it out, we'd find our SE first. So it's S divided by square root of n. 1 divided by square root of 10 is 0.3162. Again, practice, practice. Then we do x bar, 8.5, minus 7.5, divided by our SE, which is 0.3162, to get our t of 3.16. Now, normally we go to the table and we look it up to find our p-value. But in this case, we're going to do something called a critical value. So if we have t equals 3.16, picture-wise, just kind of like our z-table, z-scores before, 3.16 would be way towards the end, and we're looking for more than. That's a very small piece. But let's compare to the critical value, the t star. Now to find t star, it's 95%, because alpha is 5. Degrees of freedom would be n minus 1, which is 9. And then, if we look up 95% and 9 in the table, 95% and 9 in the table is 2.262. That's our t star. So t star is 2.262, which in the picture would be here, and then more than would be this area. So if we want to talk about critical values, a picture of our p-value would be this little picture here. Our picture of our alpha would be this area here. Our p-value, coming from our t, is smaller than our alpha coming from our t star. So the p-value is smaller, we know we need to reject HO. But some of us may be a little iffy on critical values, so you kind of want the p-value like we did before. To do that, we'll get it from the calculator. So we go to the calculator, we go to stat, over to test. This time we're doing a t-test. Still stats because we don't have the data. Mu is 7.5. X bar is 8.5. Standard deviation is 1. Sample size is 10. And we're looking for greater than. If we go to draw, it will give us a picture. Again, if you get an error at this point, it's because one of your plots is on. But this is doing it in the calculator. It will still give us our same t, or very close to it, and it will give us our p-value. So the t is 3.16, like we got, and our p-value, be careful, is 0.0058. 0.0058. So if we compare our p-value to our alpha, and be careful, 0.0058 is smaller than 0.05, smaller, so we reject HO. There is statistically significant evidence to reject HO because of our small p-value. We conclude that the average hours of work for Americans is greater than 7.5 hours per day. Now, we've proven that it's greater than, but we want to know how much greater than 7.5 is it? We know it's greater than 7.5, but what is it? That's when we do our confidence interval. So for the confidence interval, yes, it's random. We're going to assume it's normal, it is small. And we follow our formula. X bar plus or minus T star, which we found earlier. Our SE, which we found earlier. 8.5 plus or minus 0.7152 gives us 7.785 to 9.215. Now remember we said it's greater than 7.5. The whole interval is greater than 7.5. We are 95% confident the average hours of work for Americans is between 7.785 to 9.215 hours per day. And again, all the calculator steps are here for you.